Good evening, everyone, and welcome to our 12th weekly discussion session for the Physics of Nanoscale Devices NPTEL course. I am Jyotishwaran, a PhD student from the Electronics and Communication Engineering Department, IIT Roorkee. So, in this final week's session of this course, we shall be covering the following topics. So, although the lectures contain more topics and it also has a summary of the course, uh, today's session will be focused on the topics, as always, will be focused on the topics that are pertinent to the assignments. So, uh, on that note, we shall be looking at to that end, we shall be looking at strain engineered devices. This is a continuation from where we left off last week. And in that, we shall look at the notion of isoenergy surfaces and subbands. And after that, we shall have a brief discussion about thermoelectric effects in semiconductor devices and a briefer discussion of quantum dot devices. And with that, we will end our weekly discussion session. I had asked for an extra session to be scheduled so that I can do a course summary of my own. But thus far, I have not received any intimation of whether the session will take place or not. So the extra session, like assuming that I don't take the extra session, this will be the last session we have. Otherwise, I'll have one more session to interact with everyone. So, moving on. So, when we are talking about strain engineered devices, the basic idea is kind of given in this figure. So, this shows the isoenergy surfaces of unstrained silicon, so along the 100 plane, and the introduction of a tensile strain along the z-axis, and what happens to the isoenergy surfaces under that condition. So this figure gives that. So where these values come from, I will work out briefly in the next slide. What needs to be remembered is this. So before any strain was applied, so these are essentially ellipsoids. Okay, so what needs to be understood here is that each of these ellipsoids are degenerate before a uh, before any kind of strain is applied. Now, when a strain is applied, the first thing that happens is this degeneracy that exists between these six ellipsoids is kind of lifted. So these two ellipsoids have a different energy level hierarchy, and the four kx ky along the kx ky axis, the ellipsoids along the kx ky axis have a different hierarchy of energy levels. So this splitting is essentially what we call subbands. So, and we have also seen the notion of subbands when we spoke about quasi 1D, quasi 1D and quasi 2D channels. So here also the concept is more or less the same, but the origin is slightly different. So I shall briefly mention how that happens. So whenever we are talking about strain devices, especially when we are talking about, so when I say tensile strain, so tensile strain, not strain, this implies stretching of the bonds, stretching of atomic bonds. Or conversely, we can have a compressive strain. Once again. So here we have, like a compression of So there are many methods through which this can be achieved. I'm not going to go into those details here. Suffice to say, what happens is, let us say, like this is exactly as was described in the end of last week's session. So if we have a system that has, or rather I should make this longer. So what I'm going to do is, so if we have a system that's like this, which acts as the substrate, so if we have just one more layer, so it is to be assumed that this is some kind of a substrate, and on top of this, if we are trying to deposit a material that has, say, so something like this, and let me just for the sake of completion make another layer on top of this. So what should be understood here is that, like, these are not just dots in space, these essentially represent solids. So these things are kind of bonded to each other. So right now I'm just assuming that this is, some kind of a 2D rectangular lattice, but ideally speaking, we are depositing like this would be a 3D material, and on top of that we are depositing a thin layer of another material. So that's also three-dimensional. So in reality, these will be some, lattice, and considering whichever plane along which I'm depositing, we'll have, or rather, whichever plane of this material is being exposed, deposition will take place accordingly. So here again, we will have our bonds. Yeah, so we have the bonds over here. The point is when deposition occurs. So let me say, when I say deposition, essentially, when I say deposition, what I mean is red on black. So, yeah, so there is red on black. Okay, so this happens. What will happen is these bonds will kind of stretch to match the things over here. So what we will have is, I will just draw the interface layer and nothing more. So we have this. Now we shall have on top of this something like this. And so over here, these bonds are, the chemical, like the reason I'm using like relatively full lines and dashed lines here is to kind of indicate that these are, these may be two separate kinds of bonds. So just to account for that, whereas this is still going to be solid lines, and here we are going to have kind of an intermix. So here we are going to have, So let me just draw half lines here. And so this is kind of the addition between these two layers. So initially, if this was some A prime and if this was A, let me just color code this. I should have done this before. So if this is, and if this thing is A prime, now what will happen is even this will become A prime. So I have A prime above and A prime below. And the strain delta will be given by A prime minus A divided by A. So this is the strain. Okay. So, and whichever direction. So in our example that has been shown here, we are assuming that the tensile strain is applied along the z-axis. Okay. So this is the like overall picture. Now let us look at the energy in the conduction band. So if you are looking at E, so here E is in conduction band. So when I mean in conduction band, what should be understood is this E is equivalent to E minus EC, and that can be written as so Kx minus Kx naught whole squared by 2 m star plus h bar squared ky minus ky naught whole squared by 2 m star. So this is in the unstrained situation, especially true in the case of silicon 100. And finally, we will have the third axis of motion, so that is kz minus kz naught squared by 2 m star. So in general, such an equation will have, so if these were all zeros, then we will be looking at a sphere centered around 0, 0, 0. But as you can see, the 0 points for these respective systems will lie at plus minus, not plus minus, will essentially lie at, wait, am I writing this correctly? Or should it be k squared minus k naught squared? Because if I write this, then only 3 values are there. Oh, but yeah, positive and negative are symmetric. So yeah, this is fine. So essentially, this will give us to a situation where I have this kind of a these are among the straightest lines I've ever drawn in my life. So we have the x-axis, we have the y-axis, and by convention we have the z-axis. Rather, by definition we have the z-axis. So what will happen is we will have like the centers for each. So this will be our plus minus kz naught, and this is going to be plus minus kx naught. The point is kx naught, ky naught, kz naught need not be the same. So yeah. Yes, I just noticed that. Okay. So turns out I can't just lose the line. Yes. So we have this, and here, and we have some ky. So we will essentially have ellipsoids around each of these center points. So I will have one ellipsoid over here. So I'm not drawing the solid ellipsoid, I'm just shading an outline. So we have one ellipsoid over here, then we have another over here. Oops. And similarly, we'll have another one over here. And finally, we will have an ellipsoid along the z-axis as well. So what should be noted here is these are all like, yeah, although they don't at all look same, these are all essentially the same like volumes around each of these center points. Now, uh, yes. So now what we have is when a strain is applied, as I explained very roughly in the previous uh, session, K is proportional to 1 by L. So, like this is, you can see directly from the dimensions of the wave number. So, as L decreases, K increases. As L increases, K comes down. So, essentially what happens is, let us say we have this kind of a situation where a tensile stress has been applied. So, when a tensile stress has been applied, let us say along the Z direction, the values of Kz like on the same level, essentially what that corresponds to is this axis will kind of become longer. Essentially, a unit length here will have a higher value than the same length here. That implies this axis has been scaled by a fraction. So kind of the lengths increase. Like the unit point will lie farther away from the origin than the unit point lies from the origin in the x or the y directions. So because of that, the same ellipsoid will now become larger. So that is kind of what is seen over here. So this, oops, sorry. Yeah, so this expansion that we see here, that is due to the strain that is applied. Okay. And what does this lead to? What this leads to is we will have now two cases. So we will have now two effective masses. We will have ML and MT. So typically MT is less than or equal to ML, and ML will be in like 2 lobes, and MT will be in like 4 lobes. So therefore 1 over m star, or rather this shouldn't be ML, this should be m star, effective mass transverse, effective mass longitudinal. So assuming that conduction is taking place along the z direction, what will happen is these x and y lobes will actually have motion that is transverse to their existing momentum. Because along these axes, what we can understand is essentially these kx, ky, kz values are the momentum values. So along these axes, I know that the largest momentum component is along the axis on which these lobes lie. So here the force that is being applied to cause conduction is essentially transverse to the motion of the electrons, whereas here it is longitudinal to the motion of the electrons. So over here in these four lobes we shall consider the transverse effective mass, in these two we shall consider the longitudinal effective mass. So from that what we shall get is this expression 2 by ml plus 4 by mt. So this is, we can multiply and divide by 2, which implies 1 over m star effective. Yeah, as I mentioned yesterday, I would say effective mass. I will, let me just call it the average effective mass. So m star average is equal to 4 into mt plus ml divided by twice ml into mt, which implies m star average is equal to 2 into ml into mt divided by, so essentially the 4 and 2 factor will cancel out, so what we will have is ml into mt divided by 2 into ml plus mt. So we know that this is kind of 1/4 of the harmonic mean of. So if I just had ml and mt, then the harmonic mean, like, so let me quickly just make a small box here. So, and people who are familiar with their, theory of inequalities or, progressions and things like that, like essentially high school math, will know that the harmonic mean, so if I have a comma b, then Hn is equal to 2ab by a plus b. So in that notion, and we also know that am is greater than or equal to gm is greater than or equal to hn. So this inequality is true for any two positive numbers. So we have a comma b greater than 0. Geometric mean is square root of ab, and arithmetic mean is a plus b by 2. So this quantity is 1/4 of the harmonic mean, and we can show quite directly that this is actually um, lesser than even the longitudinal mass. So this quantity is actually even less than ml. So by introducing the four transverse mass laws, what we have done is we have essentially brought down the average effective mass. This implies mobility increases, and since mobility increases, it also obviously implies that conductivity improves. So even for a minor voltage, as not a minor, like a small voltage, minuscule voltage, we are likely to have larger values of currents. So that is the essential aim of doing all of this. Now this was explained before. We shall see what these. Oh, sorry. Now we shall see what implications these have with some toy examples. So uh, yeah. So now first, what has been given is we have a quantum system that is defined as an infinite 3D square well. So what is an infinite 3D square well? So an infinite 3D square well has potential of this form: v of x comma y comma z is equal to 0, 0, if 0 less than equal to x comma y comma z less than equal to some value a, or let me, rather than a, let me use L, and infinity otherwise. Otherwise. So essentially what does this mean? It means I have a cubic volume side L. Inside that the potential is 0, and outside of that the potential is infinite. So the particle is confined to be within this cubic box. So for this we know the energy is given by kx comma ky comma kz, which is s bar squared by 2m into kx squared plus ky squared plus kz square. I'm not solving this entire thing again, where kx is n pi by L, which is equal to ky, which is equal to kz. So this is the initial system. These are the energy levels. So up until here, everything is fine. So yeah, wait, did I? Okay, so this part is actually supposed to be done for the second problem. I kind of changed the question order here. But yeah, this is problem one. So this is A. Now we need to sketch the uh, energy levels. So how do we do that? So how we go about that is like so. So now I can write the complete value of E of nx comma ny comma nz rather than in terms of k's. So this is equal to h squared by squared by 2m L squared into nx squared plus ny squared plus nz squared, where nx comma ny comma nz equal to 1 comma 2 comma 3 all the way till infinity. So now all we need to do is just sketch the energy level diagram. Let us do it for like the first 5 energy levels. But what is also required here is the are the degeneracies. So the ground state, and this is true for most quantum systems, it is seldom degenerate. The ground state is usually a non-degenerate system. So almost invariably the ground state is a unique state. Like it does not, there cannot be two ground states for a system. The ground state is usually unique. So we have the ground state, which is, so this is 1 unit of energy. So I'm going to call this thing E naught. So the lowest value is going to operate. So this is E in E naught units. Okay, so this is E in E naught units. Yeah, so we have initially the lowest possible energy is 3 naught. The next lowest possible energy is one of these can be 2. So that is going to be 4 plus 1 plus 1. So that is going to be 6 E naught. So 6 over here. And we know G is equal to 1 here. But here the value 2 can be in Nx, Ny or Nz. So now that is, oops, G is equal to 3 in that case. And the next excited state is, so we can either have 2 to 1 or 3 1 1. So 221 will correspond to the case where the energy is 9 n naught, and 311 will correspond to the case where the energy is 11 n naught. So obviously 221 is the like immediate state, like the next state. So that is going to be at 9 e naught, and that again has a degeneracy of 3, and then we are looking at 9 e naught, sorry, 11 e naught, which is 311. That will also have a degeneracy of 3. So this is at 11, g is equal to 3. And after that, we will have uh, essentially what, yeah, 3 to 1. So like one of this is 3, the other is 2, the other is 1. Can it be 411? 411, it will be 18. 3 to 1, it's going to be 14. Yeah, it's actually going to be 3 to 1. But now, what will happen is when it is 3 to 1, there are 3 possible values and all permutations should be taken into account. Therefore, G in that case is going to be 6. So this is the 5th energy level that we wanted to look at. So yeah, this is it. So these are the first 5 energy levels: 3 naught, 6 e naught, 9 e naught, 11 e naught, and 14 e naught, with their respective degeneracies of 1, 3, 3, 3, and 6. So this is what was asked in question 1. Now the effective mass for this is whatever mass I defined here. It is m. So this is just m. But here this needs to be repeated in problem. Yeah, just 1 second. Yes, I'm back. So yes, so problem 1 is solved. So the degeneracy levels. So first 5 energy values are E1 is 3 naught, E2 is 6 E naught, E3 is 9 E naught, E4 is 11 E naught, E5 is 14 E naught, and this has G is equal to 1, G is equal to 3, G is equal to 3, G is equal to 3, G equal to 6. In fact, one can easily say that uh, for any nx, ny, and z, depending on what the values are, if all of them are equal, then that state is uniquely defined. So if I have, say, wait, did I consider 2, 2, 2? Yeah, I forgot that before going on to, oh yeah, so this is 1 on 1, this is 2 on 1, and this is 2 on 2, and yeah, I forgot 2, 2, 2, which would be 4, 4, 4, 12. Yeah, so that will be over here, yes, before 14. So we will have 12 E naught, which will have a degeneracy of 1, and then we will have 14 E naught, which will have G is equal to 6. So this is, so 12 E naught, where degeneracy is 1, and finally we will have the 6th energy level, which is 14 E naught, where the degeneracy is 6, 4. So now these are the energy levels and their corresponding degeneracies. So Yes. So as you can see, even here, nx equal to ny equal to nz equal to 2 actually has higher energy than one of them. Like here, this is 3 comma 1 comma 1, or 131 and 113. So one of the quantum numbers is 3 here. Here all are 2, and we find out that that is a higher energy state than the previously considered E4. Okay. So again, like that comes directly from the energy, like the expression for the energy. So this is question 1. Now, in the previous problem, now what we are saying is the potential well is subjected to a compressive strain along the z direction. So what we mean is now Lx equal to Ly equal to L, and Lz is equal to some L dash, where L dash is less than L. So if I am considering the, oops, if I am considering a Q, I mean the lines are right here, and somehow I still managed to mess it up. Yeah, so now what has happened is we have uh, Lx, or rather, since I already said that, I will say L, and now in the z direction there has been a compression. So, so let me say there has been some kind of a compressive strain in this direction. So because of that, what has happened is this thing has kind of moved down. So we are over here. This part is kind of gone. So now this is the effective length that we are supposed to consider. That is L prime. Okay, so there has been a compression that has happened. So in this case, again, nothing changes. What happens essentially is now E of nx, ny, nz, again, the form of the solution will not change, but there is going to be a small catch. So we are going to have, oops, h bar squared y squared by 2m l squared times nx squared plus ny squared plus squared y squared by 2m l prime squared l prime squared times nz squared. So this is how the energy values look. Now the reason why I sketched the first 6 energy levels there is for this very reason, so that we'll have an idea of what the quantum numbers are. So yeah, I think in red I will also write the quantum numbers over here. So this is 1 comma 1 comma 1. This is 1 comma 1 comma 2, etc. This is 2 comma 1 comma 2, and associated permutations. This is 3 comma 1 comma 1, and permutations. This is strictly 2 comma 2 comma 2, and this is 3 comma 2 comma 1, and all. associative permutations. Now what will essentially happen for this new system? So again, the energy level diagram and the degeneracies have to be plotted. So how do we go about it? We go about it in the same way as before. So sorry. First, I didn't need that long an x-axis. This will suffice. So now I'm going to like write it in greater detail. So let me also say something like, let us say L dash is equal to, what is a good number? So let me say it is 0.5 will be too bad. That will be like too much compression. So let me take this is 3 by 4 times L. Okay, so it's kind of apparent from this figure also. So if that is the case, then what are we looking at? Yeah. So in that case, E of nx comma ny comma nz is now going to be, so since that is the case, then L dash square is going to be, so this is going to have a factor of 9 by 16 here. So that will become 16 by 9, which is important. So what I'm, yeah, so I'm going to write that like this. So now that is going to be n squared pi squared not x squared. This is going to be h bar squared pi squared by 2n L squared times nx squared plus ny squared. The 9 by 16 factor can now be absorbed here, plus 4 by 3. So there will be a 9 by 16 factor in the denominator here. It will become 16 by 9 when it comes out. So 4, not 4 by 9, 4 by 3. So I just 4 times nz by 3 whole square. So now it should be easy enough to guess what happens. The lowest energy is still going to be 111. So E1 is still going to be 111, but every time nz, or rather no buts here, so that, and if I assume this quantity to be E naught, and this is in E naught units, so lowest energy value is going to be E naught into 1 plus 1 plus 16 by 9. So that is going to be 34 by 9, which is approximately what, 3.7. Yeah, yes, 3.78. So this is approximately equal to 3.7, or rather I can even say 3.8, one third. So 3.8 E naught. So right off the bat, our ground state energy has moved from some E to some E naught dash. So this is no longer at 3, this is at 3.8. Now we consider E2. Now this was supposed to be all these 1, 1, 2, or rather let me not take that as our special case. So let me take 2, 1, 1, and the permutations. But the point is, whenever Lz takes a value, its impact is more pronounced on this energy band structure. So now this energy, like what was a threefold degeneracy, will now split. There will be a lifting. So this and 1, 2, 1 will have the same energy level. However, so and that will be, so that's going to be 1 plus 4 times plus 16 by 9. So that is going to be 9 plus 36, 45 plus 16. So that's 61 by 9. So that is going to be what? 61 by 9 is going to be, or is it 54 and another 7? So that's going to be approximately 6.8. So next one is going to be over here at 6.8. So this is going to be 6.8. And here, of course, G is equal to 1. Degeneracy is 1. Now here, this is equal to, this has a degeneracy of 2. So this is G is equal to 2. So this is a twofold degenerate state. The next energy level is going to be so this is going to be approximately 6.8 E naught. Now that is going to be 1 plus 1 plus 4 times this. So that's 64 by 9. So that's going to be 64 plus 18 whole divided by 9. So that's what, 82 by 9. So that's almost 9 E naught. So that's going to jump all the way up here. And we have our first band splitting. So this is at 9. And of course, this has a degeneracy of G is equal to 1 only. So what will happen is, now you can qualitatively guess from this. The ground state has kind of moved up. Of this threefold degeneracy, one is going to move up. Of this threefold degeneracy, one is going to move up. And in general, all of these energy levels are going to move up by a certain amount. So what will happen is, out of these, one will jump up. Over here, instead of 1, 2 will jump up. So what's going to happen is, we will have above this another black line, but above that black line, similarly I will have a red line. So remember the degeneracy, it is 1, 3, 3, 1, 6. So this is the first 3, this is the second 3, and then there is going to be a third 3. I'll draw the red first, and then there is going to be the black, and oops, and then so this is how it's going to rise. So I am not going to do the whole thing. So essentially what will happen is, now there is a splitting. So this ladder here, so let me consider the case where it is 2 to 1. So it is 4, 4, 16. So that's 36, 36, 72, 88. So that's 9.8. So that's going to be close by here. And when it's going to be one of these is going to be 2, then we are going to have 64 plus 4 plus 1, so that's 5. So 45 and 64 is 109, that's 99. So that's 11 point, oh no, that's 12.1. Yes, so this is going to be 12.1 over here. So now what we will have is, we will have 2 ladders. So this is the unprimed ladder, and this is what I shall call the primed ladder. So I have E0, E1, or rather I shouldn't say E0, I will have E1, E2, E3, E4, and then what we will have is E2 prime, or rather, yeah, what we will have are E2 prime, E3 prime, E4 prime, and so on. So this is what we mean by formation of subbands. So these energy levels kind of split and there is a misalignment. And this misalignment actually ensures that certain energy transitions are forbidden. So these are what are called intervalley scatterings, or yeah. So these are called intervalley scatterings. So are inter subband scattering. So movement. So I will just say E is 3.8, E naught 6.8, E naught 9.8, E naught, so on and so forth. E prime is going to be 9, E naught, 12.1, E naught, and so on. So movement of electron or electrons from unprimed ladder to primed ladder is called intervalley scattering. And the reason that, I mean, because these energy levels are split, what happens is these intervalley scatterings are reduced. In this original case, our unstrained case, a lot of intervalley scattering could occur, which implies the electrons were free to scatter and change their momentum direction from X to Y to Z. And that is like too much of a random motion. Now, the presence of strain has kind of reduced that. So, strain engineering. So strain engineering reduces intervalley scattering. So this should be remembered always. Okay, so this kind of gives us the motivation for like why we want to do strain engineering, and we also have seen that the effective mass comes down. So we have higher mobility, we have lesser scattering. All of those things are good for ideal situations for having electron conduction in the channel. So this is the reason why we go for the strain engineered devices. So we have also seen a concrete illustration of the formation of the subbands. I will take a short, I'll be back in just a couple of minutes. Yes, I'm back. Apologies for the intrusion. So, yeah, this brings us to the end of problem number 2, and we have seen the notion of the emergence of subbands, and we have also kind of explained where and how the effect of strain is introduced into the system from an energy perspective, like energy level, energy distribution perspective. So now we shall look at the other topic, the notion of isoenergy surfaces. So over here, I just drew the figure and said, okay, now these are the isoenergy surfaces for a 3D material. So now we'll try to construct the isoenergy surfaces. So before we start, isoenergy, as you may energy is the same as is meaning same or equal energy. So this is like the equivalent or analog of the equipotential surfaces that we draw. So in electrostatics or any kind of like dynamics that we study, when we not dynamics, field theories that we study, when we have some kind of a force field, we will sketch surfaces that are equipotential surfaces where the value of the potential remains the same. So this is kind of similar to that, where instead of equal potential, we sketch surfaces that are equal energy. So those are your isoenergy surfaces. Okay, so now what is told is this. We have a system of particles that are moving in a quasi 2D environment. So this is a quasi 2D environment. So this can be like some kind of a channel, quasi 2D channel or something. But this is again a toy example. So what is mentioned is the confinement occurs along the z direction, which implies, now if we have, let me again quickly uh, yeah, draw the axis. So if we have this kind of now what is mentioned is the, so this is x, y, and z. Yes. So now what is given in the question is the particle is free to move in the xy direction. So there is some kind of a confinement in the z direction alone. So there is some kind of a confinement. So I can kind of, I can say that our particles are more or less free to move like, or rather than doing this, yeah, I think there is an easier way for me to represent that. So what is essentially happening is the particle is kind of confined in, like confined along the z-axis. That confinement is done using this kind of a potential. Now, if I were to draw just the z-axis, so this is the z-axis, and this is v of z. So this is going to look something like this. So this is a parabolic potential. Now, it is known that this kind of potential will lead to bound states. So this potential is capable of confining particles in whichever direction such a potential is applied. Got rid of the whole thing. So yeah, so we have this kind of potential. So the wave functions for this will look something like, it will look something like The ground state wave function is a Gaussian, and then the higher excited states wave functions will be this, and so on and so forth. So, like this is a well-known potential whose solutions are all well studied and so on and so forth. So, now we want to sketch the isoenergy surfaces of a surface of this system. How do we go about doing that? So, how we go about doing that? In order to do that, let us first write the energy of the particle first. So, that is, since the particle is free to move along the uh, xy direction, so it's just going to be kx squared plus ky squared, where actually kx comma plus something, but even before I write what that something is, I can write kx comma ky are real numbers. So these are real. For a harmonic oscillator, I know that the nth energy level is En is equal to n plus half times h bar omega. So this is known. So the omega is the angular frequency given here. So that is already known to us. So all we will do is we will just substitute that over here. So n plus half h bar omega, and n is equal to 0, 1, 2. So here n can take 0 value because the lowest possible energy is half h bar omega. So now we want to like look at the isoenergy surfaces. So before we consider the effect of this, let us just look at this. So let us just look at this quantity over here. So this is like if I say h squared by 2m kx squared plus ky squared is equal to some E naught. This implies kx squared plus ky squared is equal to 2m, not 2m naught, 2m E naught divided by h bar squared, and this is equation of a circle. So if nothing was there, for a 2D system, the isoenergy surfaces would be circles centered around the origin. In fact, yeah, circle centered around 0, 0. Yes, circle centered around 0, 0. Now, what will the effect of this be? So essentially what will happen is, all we have to do is the following. Okay, so wait, instead of saying that, I will first sketch this. So now, for whatever my value E naught is, whatever energy value I choose for my isoenergy surface, I am going to have kx, ky, and going to have a circle. Yes, fortunately this more or less looks like a circle. Okay, so now this is a circle with some radius r. Okay, So now this is the isoenergy surface in this case. Now what is the effect of this thing? So essentially now there are 3 degrees of freedom. So we have the like free motion in the x-axis, free motion in the y-axis, but in the z-axis now I have a series of discrete energy levels. So the lowest possible energy value is half h bar omega. So what we can simply do is, not what we can simply do, what we need to do is vary this value of n until, or rather for as long as this value remains positive. So essentially, like here I've told kx and ky are real. So this quantity is always going to be greater than 0. This quantity can never be negative. This quantity can also never be negative. So the total energy of my particle is always going to be positive. So given that the total energy is always going to be positive, I can just increase the value of n. Like initially it cannot be smaller than 0. So whatever it is, now in the new case, we are going to have, for the same energy, let us say now E naught is equal to this. So let me say E naught is equal to by 2m into kx squared plus ky squared plus n plus f into h bar omega. Now this is equivalent to saying the following set of n relations: kx squared plus ky squared is equal to 2m by h bar squared into E naught minus half h bar omega, and similarly, or 2m by h bar squared into E naught minus 3 half h bar omega, essentially n equal to 1, and so on until this comes closest to 0, as long as this is greater than 0. So this goes for all n such that E naught minus uh, E naught minus E naught minus, oh, oh no, why did I change the color? E naught minus n plus half times h bar omega. So this goes so on is greater than or equal to 0. It will go until that point. So that all depends on our choice of E naught. So each of that will give me a circle of a smaller and smaller and smaller radius. So now the equipotential surface for each value of n, I will correspondingly have a circle of a concentric circle of smaller radius, and then below that there is going to be another circle, and so on and so forth. So the equipotential surfaces, like at least when viewed along the xy plane, are going to be like this. We can be more precise, introduce the z-axis, because after all this is a like a 3D system, it's only quasi 2D. So in that case the equipotential surface will look something like this. So it is going to be yes. So The negative z-axis is not required, so we don't have to worry about that. So we have the x and y-axis. So so we will have one circle here, and so this is not at z equal to 0, but yeah, I should kind of point it out here. This is this point here. So let me quickly take the thickness all the way down. So this point here is 0 comma 0 comma half, because I'm like, this is not the z-axis, this is the n-axis, and the lowest value n can have is half, and from that it will take jumps of 1. So it's going to be 3 by 2, 5 by 2, 7 by 2, so on and so forth. Okay, so there's going to be a circle here, and then at 5 by 2 height there is going to be another circle of smaller radius, concentric. So there'll be another. What I should have done is not drawn the circle like this. What I should have done is a smarter thing. Let me just take 1 minute to sketch it so that the picture becomes clear. Rather than do this, what I'm going to do is I'm going to, yes, this will do nicely. So cone, and yes. So here, let me, and the next is going to be again concentric to this, but of a smaller radius. And the next one is going to be still concentric, but of a further smaller radius. So yeah, now I can draw the axis just on top of this. So this is the z-axis, and we have the xy axis kind of passing through this. Yeah. Oops. I somehow managed to miss the center for both. Yes. Yes. So we have the x-axis, we have the y-axis, and this is not technically the z-axis, this is the n-axis. So as you can see, the iso energy surface for this actually is a cone. So of course, not all points on the cone like fall under the like iso energy surface, but these are rings or circles that lie on the surface of a cone. So those are our iso energy surfaces. So these points here at the base, of course. So all these are the iso energy surfaces. The given system. And the structure is actually conical. So this is conical in structure. I would encourage everyone to consider different kinds of, like, binding potentials along the z-axis. You can also consider an infinite potential well and see what happens. You can consider, say, okay, now this is harmonic potential. You can also consider, although it's not technically accurate, you can consider a 1 over z square potential also. While it does not make any sense to have a 1 over z square potential in one dimension, it will still yield the kind of bound solutions, bound states. So with that also you can sketch similar surfaces, and you will see that the contour that is traced by these rings will change depending on the confining potential that you use. Use a harmonic potential, the contour is essentially a straight line, because of which we get a conical surface. But otherwise we will have other curves. In fact, if we have no binding potential, we all know that the equipotential surface will become a sphere. So in that case, the contour is essentially spherical. So the potential that is applied or not applied will determine the contour of the isoenergy surface. So that is our discussion about isoenergy surfaces. We come to our second last topic of today's discussion, that is thermoelectric effects. Again, rather than go through the formulae and the derivations, which are actually done in significant detail in the lectures, I will kind of like revise that through a problem. So, in this problem, what we are considering is our good old friend, the two-terminal device. So, we have source electrode, a drain electrode, and we have the channel that connects the two. So this is our device for consideration. So we have source, drain. Both are considered to be, macroscopic. Right now we are not worried particular, or rather we can even consider a two-terminal. Let me say this is a two-terminal nanoscale device. So yeah, this is short channel. So now the question is, what will happen when there is a temperature? Now, why do I need to know the difference between the Fermi levels? So I need to know the difference between the Fermi levels for this reason, this very simple reason. I of E is nothing but 2Q upon H into T of E into M of E into F2 minus F1 dE. Yeah, IEDE, or rather, yeah, I can drop the D. That's fine. So the like specific current at a given energy level is given by this. Now these quantities we can calculate. Like these are essentially based on the structure of our material, structure and size. So temperature does not play a role here. The only place where temperature dependence appears is in F2 minus F1. So I just want to find out what F2 minus F1 is. Now, right now there are no voltages connected to this system. So both are like kept at the same voltage. So I can assume both of these are grounded, or rather, I will not say they are grounded. The circuit is open, no potential whatsoever is applied. Okay, so now the question is, what is the difference between the Fermi levels of the two electrodes? And we are told to assume that the drain is hotter. So part A can actually be done quite directly. So at any finite temperature, so if I can sketch the Fermi function to be something like this, then the midpoint where this goes to 0.5, So this is 1, this is 0, this is 0.5. So this energy is EF, and if we have a drain that is hotter, we know that okay, so yes, yes, that would imply this will have to, I cannot curve it too sharply. Yeah, so what I'm going to do is this. Yes, I have to draw this on top of this and decrease the curvature of this thing. Yes. Yeah. So this is, so I'm going to say blue is the source Fermi function. No, not SOR. Blue is the source Fermi function, and the red one is the drain Fermi function. So no, yes. So this is how it looks. So for so now the difference is as follows. For E less than EF, we know the source Fermi function is greater than the drain Fermi function. So Fs is greater than Fd. And for EF, or rather greater than or equal to. So for E greater than EF, we have Fs less than or equal to Fd. So now what does this? So this is essentially the answer to uh, part A. So since we know the differences, we can give the sign for the function. So the difference between these two, it is going to be like if I write it as Fs minus Fd, it is going to be positive for less than for energy levels less than EF, and it is going to be negative for energy levels greater than EF. Now what is this going to tell us about the sign of the Seebeck coefficient? So what is the Seebeck coefficient? That is why I said I'm not going to ground these electrodes. So the Seebeck coefficient is essentially this. If I have this kind of a setup, and if I say this is at temperature T1 and this is at T2, then the question is, what is V open circuit as a function of temperature T1, T2? So this is the Seebeck effect. When I have a temperature difference across the two electrodes, a potential difference arises simply as a result of the temperature difference. So now where does the potential difference come from? That is apparent from this figure itself. Now, if this is the case, This implies the probability of finding an electron with energy E is greater in the source than in the drain for energies less than the Fermi level. For energies greater than the Fermi level, the probability of finding an electron with energy E is greater in the drain than in the source. So, what does this mean? So, this means there are essentially more electrons above the Fermi level in the drain and more electrons below the Fermi level in the source. And typically, when we consider electronic conduction, we are worried about electrons above the Fermi level. So that is higher in the case of the drain and lower in the case of the source. And as the temperature increases, this difference, this disparity will keep increasing further and further and further, which implies as the temperature increases, electrons will tend to move from the drain to the source. Okay, so let me quickly get my slide here, drag it down here, and so part B for E greater than EF, Fs less than or equal to Fd implies probability of finding electrons in drain is higher. And conversely, yes, nothing, no, I mean, converse is not yet required. I will talk about the converse in a minute. So, this implies in this temperature setup, the electron concentration is higher in the drain than in the source. Therefore, electrons will tend to diffuse from source to drain. Sorry, not source to drain, from drain to source. Yes. So this is the first case. Second case, if we are talking about a material that is hole rich, then at higher temperatures, the source is more liable to have, essentially there are fewer electrons above the Fermi level in, there are fewer electrons above the Fermi level in the source, which implies there are more holes, there are more vacancies. So what this means is, so what this essentially means is, yeah, drain to source as temperature increases. Similarly, holes will drift. I shouldn't say drift, I should say diffuse. From yeah, apologies for the interruption. So yeah, as I was saying, holes will diffuse from source to drain as temperature increases. Why? Because the very fact that electrons move from here means this region becomes hole rich. So that can also be seen as a transport of holes from the source to drain. So yes. Now what we need to understand is our convention for current. This is positive current. So this is positive current. And we always, like by convention, positive current is whole current. So if current moves from source to drain, if holes move from source to drain, we have a positive current. If electrons move from drain to source, we also have a positive current. So what needs to be understood is this potential. As temperature increases, I will get a more and more positive potential in the case of a hole rich material. So, and similarly, when we have a electron rich material, we are going to have a more and more negative potential. Therefore, the Seebeck effect is positive for a p-type material and it is negative for an n-type material. Because again, what we are trying to do is we are trying to move electrons from here to a place that is actually like it. How do you, yeah. So it has more electrons than, oh sorry, I shouldn't say it has more electrons. So essentially, as I'm increasing this temperature, more and more electrons can move from the drain to the source. Like as the drain gets hotter and hotter and hotter. Whereas as the drain gets hotter and hotter and hotter, more and more and more holes will form over at the source side, which will lead to the conduction of the whole current. Okay, so this is a derivation. Similarly, you can also look at the Peltier effect. The energy transfer there is explained in the slides. So I'll just simply direct you there. And if you understand those things, you should be more or less, not more or less, you should be more than comfortable with answering the associated assignment questions. So with that, we come to the final topic of today's discussion, which is quantum dot devices. So yeah. So now over here, what we are going to do is we are going to take a sample problem and we are going to look at some properties of quantum dot devices. So first and foremost, so what we are doing is we have a, yeah, I shouldn't have written quantum well here. Technically this is a well, but I mean for our purposes of discussion, this is a quantum dot. So the energy is given by En is equal to minus 25 by n squared. Of course, I should also mention that n is equal to yeah. So it can be 1, 2, 3, and so on. And what is said is each of these energy levels can accommodate up to 2 electrons. So this is very much like an artificial atom. So over here, essentially what I'm saying here is, like the long and short of it is that this system is behaving like an artificial atom, which is kind of what we expect when we set up quantum dots. Okay, so and we are told that the vacuum energy is at zero. Yes, it's not at 0 volt. I should have said it's at 0 electron volts. So 0 electron volts is considered to be the vacuum energy level. So first question is, what is the ionization potential of this quantum dot? So ionization potential, just one second. Yeah. So the ionization potential, let me make a new slide here, drag it down. So ionization potential is like typically ionization potential depends on the number of electrons that are present in the system. Since I have not mentioned that, essentially what we have to do is take E of 1 minus E infinity, or rather it's the other way around. It is E infinity minus E of 1 divided by charge of an electron. So now that is going to be, now E infinity is where n tends to infinity, that value is 0, and E1 is 25, so this is equal to 0 minus of minus 25, which is 25 electron volts divided by E, so that is equal to 25 volts. So that is the ionization potential. So if I have an electron that is trapped inside this well, with a potential of 25 volts, I can be rest assured that whatever electrons are present in there will all move from the dot to the other electrode. So this kind of gives us the switching potential for taking electrons from the source through the quantum dot into the drain. So that figure comes from the ionization potential. Now the second question that is asked is, if the dot is occupied by 7 electrons, what is the value of the Fermi energy and how will it change if the dot contained 8 electrons? Now this was something I actually spoke about like way back in week 3. I said we will look at it more later, so now is the time. So we have the system where we have like, this is our quantum well which gives the quantum dot, or rather which represents the quantum dot. It doesn't give us anything. So I have minus 25, and then the next energy level is minus 25 by 4, that is 6.25, and then we have minus 25 by 9, that comes out to be 2.8, yeah, approximately. So that's going to be further closer. So minus 2.8. So these are all electron volts. So this is energy in electron volts. And after that we have 25 by 16, that comes out to be essentially 6.25 further divided by 4. So that will be 1.5 plus 1.16, so that's going to be 1.625, yes. So that is going to be even closer. So this is minus 1.625, and after that we will have minus 1. Minus 1. So these are the first 5 energy levels. So what has been told is, initially the system is occupied by 7 electrons. So initially we have an electron here, 2 electrons here, 2 over here, 2 over here, and 1 over here. So now the question is, what is the Fermi energy? So EF, like we can either define it as the highest energy, no, like typically we define it as the highest energy an electron can have in a system at T equal to 0 Kelvin. Oh yes, what should be mentioned here is, so assume T is equal to 0. Or rather I will write that up top. So we have to assume that the temperature is 0 Kelvin through and through. So we are not looking at any finite temperature examples. So Fermi level is the lowest energy. It is the lowest energy a new incoming electron may possess. So this is the catch. Like if I want to add one more electron to the system, what is the lowest possible energy it can have? So in this case, since 7 electrons are already there, I can introduce an electron at minus 1.625. So that is the lowest possible energy an electron can have. Anything lower than that is unacceptable. So what I will do is, no, I don't have to do anything. So in this case, therefore, EF is equal to minus 1.625 electron volts. Whereas if there are 8 electrons, essentially instead of this, if I say this state is also filled, just one second. Yeah, apologies for the interruption. Yeah, as I was saying now, this is case 1. So where we have 7 electrons. So this is for n equal to 7. Similarly, if we had n equal to 8, now the figure has changed. So now there are 8 electrons. Now the lowest possible energy an electron can have is actually minus 1 electron volts. Therefore, in this case, the lowest possible energy is equal to minus 1 electron volts, which implies the Fermi energy is equal to minus 1 eV. So this is part B. Part C is about the quantum capacitance. So going back, part C says the quantum dot initially contains 9 electrons. Now the question is, 2 more electrons are introduced. What is the capacitance? So using this problem, I will give a brief introduction of the, or rather brief definition of the quantum capacitance in a quantum dot. So essentially what we have is, typically in a capacitance. So what do we mean by a capacitance? So capacitance is delta Q is equal to C times delta V. So this quantity is our capacitance. So that is the essential, like most basic elementary definition of this. Now what we can do is, I can multiply by delta Q on both sides. So now I will have delta Q whole squared is equal to C times delta Q times delta V, and this quantity is actually delta E. This is the energy. So this is C times delta E. So this is where we get the definition that uh, capacitance is essentially this divided by Q squared, like the total energy divided by total energy change, or rather delta Q C delta V. Oh yes. Huh. So what I will do is I will consider the energy change Q squared by 2C, right? Yes, delta E is Q squared by 2C, and therefore, so essentially, yeah, I should not have just written this. So I should have written this as proportional to this, which implies C is proportional to, yes, delta Q squared divided by delta E. So this is another way of looking at the capacitance. So we can either look at it in terms of the voltage change or in terms of the energy change. So now what has been told is the system has 9 electrons at t equal to 0. That's why I said assume t equal to 0. So if there are 9 electrons, then up to this it is filled. Okay, so initially my system is, so we have minus 25, minus 6.25, and then we have minus 2.8, minus 1.625, minus 1, and above that is 25 by 36, which will come out to be, how much will it be? So 25 by 36 is going to be, let me quickly calculate that. Yeah, it will come out to be 0.69. So this is going to be minus 0.69. So the thing is, I have energy level here, energy level here, energy level here, here, and here, and there are 2 electrons here, 2 electrons here, 2 here, 2 here. This is 8. The 9th electron is over here, and the next energy level is empty. So now 2 electrons are introduced, which implies one of them is going to come in here and the other one is going to come in here. Therefore, the energy change in the system is, so the highest energy level was minus 0.1, sorry, minus 1. So from minus 1, I had to do the work of another minus 1, and then, so delta E is equal to minus 1 minus 0.69, which is equal to minus 1.69 electron volts. So this is the amount of energy, amount of work that was done to introduce these two charges. Now the capacitance is exactly this. It is, yeah, it is actually the average energy per electron. Okay, so yes, so I should have also done that into one thing. Yes, so that will, so here n is number of electrons. Okay, so per unit charge, like essentially capacitance is a coulomb per volt. Okay, so 1 Faraday is essentially 1 coulomb per volt. So that is 1 Faraday. So is it 1 Faraday or 1 Farad? 1 Farad, sorry, not Faraday. 1 Farad. Faraday is magnetic flux. Apologies. So this is the energy change. So on an average, so E average is minus 1.69 by 2, so that will come out to be 0.845. minus 0.845. So 845. Now what we have to understand is, if I assume this to be my base energy level, minus 25 to be my base energy level, this is going to be 25 minus 0.845. So the average energy that needs to be provided is going to be 24.155. Yes. Okay. Which is equivalent to 24.155 electron volts. Okay. So now this divided by uh, like no times n. I'm sorry. It should be 1 by n. It should be multiplied by delta. Yes. Into delta n, because delta n will be over here as the average energy. Okay, so now C quantum is equal to 24.155 divided by, I'm sorry, it is, so q squared, there are 2 electrons. Now that 2 factor has arrived here already. So all I have to do is take q squared. So that is essentially e squared divided by 24.155 ev. So now this is going to give us a quantum capacitance of around, so as you can see, the capacitance is going to be very, very small in this case, which again is expected. So this is going to be essentially like, this is an electron volt, so those things will cancel out. So what we will have is uh, yeah, so this is going to be 6.63 into 10 to the power minus 21 farad. So now that is actually how much? So like nanofarad is 10 to the power minus 9, pico is 12. Yeah, so you can guess. So this is like even below atto. Atto is, so I think this is either yocto or zetto farad. So yeah, this is essentially the quantum capacitance for this dot. But what should be understood is, typically we don't like we aren't at this point. Like usually in our quantum dots, like when we do our energy tuning and everything, we usually tune it at significantly higher voltages. We don't tune it very close to the ground state of our system. A quantum dot usually has a lot of electrons filled. So because of that, as you can see, the energy keeps increasing further and further and further. Like as I keep adding more and more and more electrons, more energy will be spent. So the average energy will also keep going up. Therefore, the capacitance value will also keep increasing. But even then, quantum capacitance is always going to be a very small value. And that is actually a good thing, because if we again look at this picture semi-classically, then the capacitance also gives us kind of a time frame, because R times C is the time taken to charge a capacitor. This is such a small capacitance, which implies the time taken for the electron to move from the source into the dot is actually very small. So this gives us an indication that these devices can actually work with, can be used for high-speed applications. So that is the end of this problem. So with that, we come to the end of today's discussion, this discussion for week 12. I'd like to take this opportunity, like if it so happens that there is not, I mean, I'm unable to take an extra session. I would like to emphasize that as far as this course is concerned and the exams are concerned, focus more on the middle part of this course. So focus on the transport theory, focus on MOSFET models, focus on the Fermi integrals, what kind of Fermi integrals are applied where. So pay attention to those things, and more than numericals, look at the concepts. Try to understand the concepts because more questions will be conceptual than numerical, as has been the case with the assignments. Like approximately 25% of the questions are numericals, and the rest of them are actually either derivation based or concept based. So the aim of this course is not to do very rigorous work. It is to kind of give us a feel just like this question. So here I kind of did a rough derivation to show that the capacitance, quantum capacitance of a quantum dot is going to be very small. And from that we got some conclusions. Similar derivations and calculations have been done in the weeks prior also. So what should be taken away from this course is the spirit of those derivations and the rationale, the reasoning that has been uh, adopted behind those methods. So that is the first and foremost thing that needs to be focused on, even from an exam standpoint. And even in the long run, understanding those things will lead to better insights into the field of nanoscale devices and what kind of parameters one would need to choose, what kind of technologies one would need to adapt, and which kind of devices are best applied, so on and so forth. So I thank everyone who has followed these videos for following it, and I hope it has been helpful to all with the helpful in understanding this course better. And I wish everyone the very best for your upcoming examinations. Thank you.